Today's lesson is starting Chapter 7, so 7.1. Chapter 7 is on a new type of way of comparing figures. We've talked about congruency before, where two figures have the same shape and the same size. Now, this chapter, with Chapter 7, we're going to talk about a new concept called similarity, which we'll get to later. But essentially, things can be the same shape but a different size. And to figure out how much bigger or smaller a shape is compared to another one that is similar, we need to use ratios and proportions. So that's why we're going to start out Chapter 7 with ratios and proportions. So that by the end of the day, you'll be able to do the following things. You'll be able to use facts about ratios to solve proportions, to therefore identify equivalent ratios, write equivalent ratios, and finally find the values using ratios and proportions. Alrighty, so we've been talking about ratios. Let's start with the definition. A ratio is simply a comparison of two quantities by division. So you can write it in three ways. So for example, every fraction is a ratio. A over B is comparing the quantity of A in the numerator to B, that in the denominator. So you can just write a ratio as a fraction. You can write a ratio as with a colon, so in other words saying A to B, or you can just say the words A to B. All of these three things are ratios comparing two quantities by division. And in all of these cases, B can't be 0. You can't have a fraction with Z as a denominator. So again, if you think about if this is comparing two quantities by division, imagine that we are comparing the number of the genders of the people in our classroom, and for every one boy, we have 3 girls. Okay, that's a ratio that makes sense. For every one boy, we have 3 girls. You could say for every one boy, we have 2 girls. Or you could say, in other words, you could say if you have one boy and 3 girls, then you could say, well, 1 out of every 4 students is a boy. If you had a different ratio, you could say 1 out of every 2 students is a boy, or even 1 out of every 1 student is a boy. But you couldn't say 1 out of every 0 students is a boy. That would make no sense mathematically, and that's why you can't have B in this equation, B, or in this expression, be 0. You can't have something divided by 0. And then finally, like a fraction, we need to write a ratio in its simplest form. So if we have the ratio of 5 to 10, we can reduce that and simplify that to be 1 to 2. All right, and they can be shown in different ways. So again, you can use the colon as a separator, you can use the line for a fraction as a separator, you can use a decimal or a percentage. All of these are, again, comparing two quantities by division. So let's go back to the example I said before. Imagine that for every boy you have in class, you have 3 girls. You could say the ratio of boys to girls is 1 to 3. You could do that another way and say that 1/4 of the class are boys and 3/4 of the class are girls. The ratio of boys to girls is 1 to 3. The ratio of boys to people in the class would be 1 to 4. So you'd call it 1/4. You could take that 1/4 and make it a decimal, call it 0.25. So 0.25 of the class is boys. Or you could make that a percentage and just say 25% of the class are boys. But all of these ratios are saying the same thing. Again, in our class, for every 1 boy, we have 3 girls. All right, let's do an example problem using a colon as a way to show a ratio. And we can use example problem number 1 here. This is telling us that there's a bonsai bald cypress tree is a small version of a full-size tree, and I have a picture over there. It's 15 inches tall, I can see from my diagram. And a Florida bald cypress tree called the Senator stands 118 feet tall. What is the ratio of the height of the bonsai to the height of the Senator? All right, so to do this, we need to compare these two quantities, the two heights, to make a ratio. However, the first problem is that the bonsai tree is in inches and the Senator tree is in feet. So if I want to compare them, I have to compare apples to apples. I have to use the same ratio or the same units. I can't compare inches to feet. So the first thing that I'll do is I'm going to express them both in the same unit So I'll convert the 118 feet to inches by multiplying by 12 inches per foot. So when I multiply 118 feet by 12 inches per foot, you can see that I end up with that senator tree is 1,416 inches tall. Now that I have them both in inches, I can do the actual ratio. The height of the bonsai tree is 15 inches. The height of the senator is 118 feet, which is 1,416 inches, like I just said. So the ratio would be 15 to 1,416. However, I can reduce both of those numbers by 3. You can see 15 can be expressed as 3 times 15, and 1,416 can be expressed as 3 times 472. So if I then get rid of the units of inches and get rid of the extra 3, I see that my ratio is 5 to 472. So the ratio of the height of the bonsai to the height of the senator is 5 to 472, or for every 5 inches of bonsai tree, we have 472 inches of the senator tree. All right, let's do a different problem here, and this is for the school marching band is going to, as a fundraiser, is going to buy pots of tulips and pots of daffodils. They plan to sell a total of 120 pots of flowers. They know that the ratio they want to buy is for every 2 pots of tulips, they want to buy 3 pots of daffodils. And the question is, how many pots of each type of flower should they buy? All right, so first of all, if we think about this, that the ratio of pots of tulips to pots of daffodils is 2 to 3, then it must be in the form of 2x to 3x. Maybe x is 1, and I'm going to buy 2 tulips and 3 daffodils. Or maybe x is 2, and I'll buy 4 tulips and 6 daffodils. Or maybe x is 10, and I'll buy 20 and 30. Rather than, however, just putting in numbers and coming up with something that adds up to 120, what we can do is let's just first of all set that 2x is the number of tulips and 3x is the number of daffodils. Then we recognize that those two numbers, the number of tulips plus daffodils together, must equal 120. So I can write that as 2x plus 3x equals 120. So I can solve that to find out that x equals 24. Now that I have x equals 24, I can go back and substitute in to find out the number of tulips and daffodils. Since tulips is 2 x's, that's 2 24s or 48 pots of tulips, and 3 x's or 3 24s is 72 pots of daffodils. So in the end, the band members should buy 48 tulip pots and 72 daffodil pots. And this is the kind of math that actually happens all the time in retail, right? If you own a store and you sell whatever Doritos and Cheetos, you need to have a sense of what the ratio is of how popular Doritos and Cheetos are. If you get that ratio wrong, you'll end up with a store full of one of them and not the other. So if you come up, if you get that ratio wrong and you end up with a shelf full of Doritos and no Cheetos, and then I, as your customer, walk in to buy Cheetos and you don't have them, well, you've lost a sale and you're wasting all that extra space with Doritos you don't need because you have too many of them. And so retailers are constantly trying to reevaluate what the ratio is of the popularity of their products so that they can staff their shelves correctly. And so this is actually a math problem that people do all the time in retail, this type of thing. All right, we've talked about ratios. What is an extended ratio? Well, again, a ratio is a comparison of 2 quantities by division. An extended ratio is simply a comparison of 3 or more numbers. So for example, you could have A to B to C. So in our last problem, we had daffodils and tulips. Imagine if we also wanted to sell roses. We would need the ratio of roses to daffodils to tulips rather than just a regular ratio of 2. And so again, you can compare the ratio as A to B to C. And of course, when you do that, it gives you individual ratios of A to B, of A to C, and B to C. It gives you those ratios right there. All right, we can use an extended ratio to try to solve problem number 3. The lengths of the sides of a triangle are in the extended ratio of 3 to 5 to 6, and the perimeter of the triangle is 98 inches. What is the length of the longest side? Well, to do that, again, let's draw a triangle, And now let's draw the sides. We know the ratio of the sides is 3 to 5 to 6. So the sides must be 3x, 5x, and 6x. I don't know what x is, but I know whatever it is, if I put that into that triangle, it'll stay in the ratio of 3 to 5 to 6. Now what I know is that the perimeter is 98. So that first side 3x plus that second side 5x plus that third side 6x, together that must equal my perimeter of 98. So when I simplify that or combine my terms, that's 14x equals 98. If I divide by 14, I get x equals 7. Now we're supposed to find the longest side. So the longest side is 6x. So if I substitute in 7 for x, I get 6 sevens, which is 42. So I know the longest side of this triangle, 6x, would be 42 inches in length. All right, when I have some ratios, I can have ratios that I have to determine are two ratios equal to each other. To do that, I can use what's called the cross products property, or we often just call it cross multiplication. And so an equation that has two ratios is called a proportion. The first and last numbers in the proportion are the extremes, and the middle two numbers are the means. So what I can do is I can show that the products of the extremes is equal to the product of the means. So in other words, if I have A over B equals C over D, where again, because we have fractions, B and D can't be 0, then when I multiply those red numbers, the extremes, and get AD, and I multiply those blue numbers, the means, and get BC, I know that the products of those two things, AD and BC, are equal. Okay, let's do an actual example. If I show you that 2/3 equals 4/6, well again, the extremes multiply to 2 times 6, which is 12, and the means multiply to 3 times 4, which is 12. 12 equals 12 because we started out with a ratio 2/3 that was equal to another ratio 4/6. And as I said above, a proportion is just two equivalent ratios form a proportion. And equivalent ratios have the same value. When two ratios have the same value, we say that they are proportionate, meaning that their values are the same. All right, let's solve some proportions. So to do this, we're going to use our cross product property or our cross multiplication. So for this one, what we can see is that 6 times 4, the product of my extremes equals the product of my means, 5 times x, using my cross products property. Multiply that out and divide, and I get that x equals 24/5. If I wanted to, I could call it 4.8, but generally in algebra, we just leave it as a fraction, in this case, 24/5. All right, let's try b. So for b, again, I'm going to multiply using my cross products property. So 3 times y plus 4 equals 9 times y. So 3y plus 12 equals 9y, subtract 3y from both sides, divide by 6, and I get y equals 2. So for this one, the value would be 2. All right, we can always solve proportions, always solve ratios and proportions using cross product multiplication. But it's easier to, if I use these these properties of proportions, having these three properties of proportions can allow me to solve problems much more simply than if I have to cross multiply every time. And I'll show you that in a moment here. But let's go through what these three properties of proportions are. The first is that you can write the reciprocal of each ratio. A reciprocal, remember, is just to flip a fraction over. So A over B becomes B over A. So if I have A over B equals C over D, and again, it tells us that all of these are not 0 for this purpose. Okay. If I have A over B equals C over D, I can say that's equivalent to the reciprocal of A over B is B over A, and the reciprocal of C over D is D over C. So I can see that if the red ones over the blue ones, if A over B equals C over D, then the blue ones over the red ones are also proportionate. B over A equals D over C. Let me show you an example using actual numbers here. if I told you that 2/3 equals 4/6, which is true, when I take the reciprocal of both, I get that that's 2/3, that's 3/2 equals 6/4, which is also true because I used the first property of proportions, which is that we can write the reciprocal of each ratio. The second property of proportions is that I can switch the means. So if I have A over B equals C over D, I can just switch that B and that C here. So I can say that A over C equals B over D. Again, let's do an actual example problem here. Let's do the same one we did before. 2/3 equals 4/6, which is true. If I switch the 3 and the 4, I get 2/4 equals 3/6, which is true. Both of those would be equal to 1/2. So by switching the means, I have kept the ratios proportionate. The final property of proportions is that in each ratio, I can add the denominator to the numerator. So in other words, if A over B equals C over D, I can say that A plus B, adding B to that numerator on the left, is equivalent to C plus D over D by adding D to the numerator on the right, because in each ratio I've added the denominator to the numerator. Let's again use our same example of 2/3 equals 4/6. If we do that and then we add 3 to the left and 6 to the right, we get 5/3 equals 10/6, both of which are equal to 5/3 or 1 2/3. So yes, once again, that ratio is proportionate by following, in this case, the third rule of my properties, which is that I can add the denominator to each numerator. Right, let's do some problems using these properties where you can see that how much easier problems are if you use these properties. So in this first question, we have a diagram on the right which has a triangle, which has, as you can see, one side is 7 and then with a portion of y there, another port, and then the top is 6 with a portion of x there. And it tells us that the ratio of x to 6 is proportionate to the ratio of y to 7. Those ratios form a proportion. What ratio completes the equivalent proportion of x over y? What is the ratio of x over y? All right, well, we can do this two different ways. The first is we can just use the proportions that we just learned here. If x over 6 equals y over 7, as it says as given to us, well, I can simply just use my second property of proportions and switch the means. So instead of saying x over 6, I'm going to say x over y, and that's going to equal 6 over 7, which is what we're trying to find. So the answer would just be 6/7. The other method, if I didn't want to use those properties, is I can always just do cross multiplication. So once again, if I have x over 6 equals y over 7, I could cross multiply and get 7x equals 6y, and again, what I want to get is x over y, so to do that, I would divide both sides by 7x. Then when I do that, the 7's on the left cancel and the y's on the right cancel, so I'm left with x over y equals 6/7. You'll see I get the same answer both ways. It's just method 1 required literally one step. Method 2 required multiple steps, including my having to realize that I'd have to divide both sides by 7y. So you can do it both ways. It's just that in this case, following the proportion, in this case, proportion, the rule of proportion number 2 is significantly easier. All right, the same thing is true for these next couple problems here. Once again, if I have x over 6 equals y over 7, it's the same ratio as before. What ratio completes the equivalent proportion? Justify your answer. All right, so again with A, what I see here is that I've simply taken the reciprocal of the fraction on the left. So I could just do the same thing to the right. Take the reciprocal of the fraction on the right, or the ratio on the right, and the reason I can do that is because of property number 1. That if A over B equals C over D, that's the equivalent of taking the reciprocal of each. B over A equals D over C. So once again, this problem can be done in literally one step. The final problem, 6b, once again, I'm using that ratio on the right, in this case y over 7, except you'll see I've added the denominator to it. I've added 7 to it. So I could do the same thing to the ratio on the left by adding 6 to it. And so now I have completed the equivalent proportion, in this case by using property number 3, by adding the denominator to both, by adding each denominator to each numerator. I still have a ratio, I have a set of ratios that is proportionate. All right, let's go through a couple of our objectives today and go through some IXL problems that we have for homework here. So the first one is to identify equivalent ratios. So let's do an actual IXL problem from the IXL identifying equivalent ratios, which is AUE. This is asking us, are the ratios of 6 to 2 and 6 to 2 and 3 to 9 equivalent? Do they form a proportion? So to do that, I'm going to rewrite them as fractions. So 6 over 2, I'm going to write as 6 over 2, and the ratio of 9 to 3, I'm going to write as 9 over 3. Then I'm going to simplify those. So 6 over 2, is that equal to 9 over 3? Well, 6 over 2 is equal to 3, and 9 over 3 is equal to 3. Are those equal? Yes, of course they are. So the answer is yes, these must be equivalent ratios, because when I simplify them down, they're both equal to the same thing. I could also, instead of simply simplifying, I could use cross multiplication. So if I have 6 over 2 equals 9 over 3, that 6 times 3 is going to have to be equal to 9 times 2. Are those equal? Well, 6 times 3 is 18. 9 times 2 is 18. Yes, those are, of course, equal. 18 does equal 18. So yes. And this also shows us that these ratios must be equivalent. So whether I used method 1, simplifying, or method 2, cross multiplying, the answer to this question would be yes. All right, let's look at our second objective for today, which is, can I write equivalent ratios? And we'll go through an example problem in IXL's write equivalent ratios in RW6 as the code. All right, this one is asking me, find the number that makes the equivalent ratio of 9 to 4, x to 44. Okay, so number 1, I can just rewrite these fractions. So 9 to 4, I'll call as 9 over 4. And this one I'm going to call x over 44. Now I can solve using cross multiplication. So once again, 9 times 44, that has to be equal to 4 times x. 9 times 44 is 396. That's equal to 4x. Divide by 4, and I get x equals 99. So the answer would be 99. The ratio of 9 to 4 is the ratio of 99 to 44. All right, the final objective we have for today is to find the value using ratios and proportions. And we're going to do that with an example problem from IXL's ratios and proportions, the code of which is 8EU. All right, it's asking us, are these two ratios proportion? Do they form a proportion, 8 over 5 and 11 to 7? So if they form a proportion if the equivalent ratios have the same value. So the first thing I could do is put them to have a common denominator, and then I can compare the numerators. So are those equal? Again, if I multiply the one on the left by 7 over 7 and the one on the right by 5 over 5, that's going to give me a common denominator of 7 times 5, 35 on the bottom, and then the denominator. So when I do this out, these two things, are they equivalent? 7 times 8 is going to be 56, and 7 times 5 is 35. So I've got 56 35ths. Is that going to be equivalent to 11 times 5 is 55 35ths? So is 56 35ths equals to 55 35ths? The answer is no, they are not. So they would not be, they're very close, but no, they are not, they do not form a proportion. The second method I could use would be cross multiplying. So if I cross multiply, I've got 8 times 7. Is that going to be equal to 5 times 11?
Are those equal? Do that out, and I've got 56. Is that equal to 55? Again, they're very close, but no, they're not equal. So the answer would be no, these two do not form a proportion.